All right. Bismillahirrahmanirrahim. Assalamualaikum and good evening. So today we're going to look at a new topic, which is classification and regression tree. Right? Classification and regression tree. So this is another type of supervised machine learning. Right? So this is the topic that we're going to discuss. Not all today. Maybe part of it by today, and another half we're going to continue next week lah. So we're going to look at what is tree-based method, classification and regression tree, on regression tree and classification tree, overfitting, pruning, and assemble techniques. So, tree-based method is a family of supervised machine learning for classification and regression tasks lah. Right, so it actually built a tree-like structure. Right, you will construct a tree-like structure for deciding the target variable, class, or value according to the features. Right, so there are many types of decision trees. So this is the original one, decision tree. Right, so in decision tree is a graphical presentation of possible solution. It will start from root nodes, right? Root nodes, and we're going to split the root node into two parts we call as internal nodes, right? And we're going to end to leaf node. Right? The end product will be the leaf node, right? So the extension of decision tree is bagging. We have extensions such as bagging, random forest, boosting, gradient boosting, and XG boost. So bagging, random forest, and boosting, all of these fall under assemble method, right? So bagging will apply bootstrap aggregation, right? And then random forest also extension of bagging, but instead of measuring the correlation in bagging, random forest will decorrelate the trees, right? And will grow more than one tree. And boosting actually we build several trees based on sequential method. So this one we will discuss next week lah, right? So now, as I said just now, decision tree is a non-parametric supervised learning algorithm. It means that it can cater for classification and regression tasks. So what is the parametric supervised machine learning? Parametric supervised machine learning such as linear regression, semi-supervised logistic regression, and so on. So this is a non-parametric, means that it does not care whether the data is normally distributed, equality of variance assumed or not, right? So it's a non-parametric supervised machine learning. It's a distribution-free techniques, right? So it can cater for classification and regression tasks. So classification tasks, we already learned that method in naive Bayes, right? Logistic regression, linear discriminant, KNN, support vector machine, right? For regression tasks, we learn in logistic regression and linear regression, right? Right. So if the assumption in linear regression is not met, such as the linearity of assumption, normality of the error is not met. So if you're still interested to proceed with regression, you can consider regression tree, right, for regression tasks. So it's a hierarchical structure and tree structure which consists root node, right, branches, internal nodes, and leaf nodes. So basically, we're going to look at from bottom down structure, from the root node to the leaf. Right, so the tree that we're going to deconstruct, starting from the root node to leaf, is a bottom top procedure. Right. So as I said just now, regression tree-based method can cater for regression task, right? Regression task is basically we have a numerical output. A dependent variable is numerical. Classification task, dependent variable is binary. So it involves stratifying or segmenting the predictor space into several regions. So in this method, we're going to segment the predictor or input variables into several regions, right? Into several regions. So then we can do prediction, right? So to split into several regions, so that we will learn some splitting rules lah. For regression tasks, we will use variant reduction method and F-test method. For classification tasks, there are three methods available, such as chi-squared log-worth method. Another one is entropy method and Gini index method lah. So this is an example of tree diagram, right? We start with a root node. So this is a root node, and this is a child node, or we call as internal nodes. Internal node, and the last outcome, this is what we call leaf node, right? Leaf node. Okay. So this is the structure that I explained just now. We have a root node, child node, or internal determine which variable to be a root node, right? Which variable to be a root node. So the root node variable is important variable for the prediction lah. So this is example of classification data set, right? I think this one kita dah tengok dah. Before this, we have X1, X2, X3, X4. We want to predict play tennis, whether yes or no. This is the classification task, right? Now let's look at the next part, right? So classification tree is a hierarchical way of partitioning the space, right? So we're going to partition the space in hierarchical way lah. So it start with the entire space and recursively divide into smaller regions. So start with the entire space, and then we're going to split it into the smaller region, right? Until the smallest one lah. Until we got the leaf and decision. So this is for example for classification method, where the leaf is either the category of the class of the dependent variable, either small or large, merit or single. And this is example of outcome or the leaf for regression task, right? Where we're going to get the numerical value lah. Basically, for leaf, we're going to look at, we're going to take the mean of that data, that category. So this is the advantage and disadvantage of classification tree, right? What is the advantage? Easy to explain. Right? Compared to linear regression or conventional way, we have a model, we have equation, and this one, we can easily look at the diagram and explain the predictor and outcome. Tree can be displayed graphically and easy to interpret lah. And easy to handle qualitative predictors without need to create a dummy variable. As in linear regression, if you have a categorical variable input variable, then you need to create a dummy variable into the model, right? But in tree diagram, we don't need to create a dummy variable, right? So the disadvantage is not competitive compared to the best supervised learning approach in terms of prediction accuracy lah, right? So it's very non-robust compared to others classifier, right? So now, regression. So step, how to build regression trees. First, we need to divide the predictor space into distinct region, such as region 1, 2, 3, and so on. And then for every X that fall into that particular region, we make the same prediction. Where basically, we're going to measure mean and standard deviation and mean square error, right? Right, let's look at this example. Example number 3, regression trees. So this is what we call as a partition space. This is partition space represent the region that split from the root nodes, right? And this is the tree diagram, right? So let's say in test or in exam, I'm giving you a partition space like this, right? This is partition space, and I want you to create or to develop or construct a tree diagram. So how to do that? First thing, look at this one. We have two variables, x1 and x2. x1 on x-axis, x2 y-axis. So we look at the region that split or completely separated between two regions, right? The line that separate two regions, the complete separated. That means it has a complete line to separate two regions. So if you look at this one, we have line x1, t1, x1 at t3. So we have two lines that separate two regions, right? So let's consider the first separation part. Let's say we take x1 less than equal to t1. So let's say we take t1 as a root node, right? So anything on the left hand side can be split by x2, right? On the right hand side, it can be split into two regions, either more than t3 and less than t3. For example, let's say kita draw the graph. So the first, let's say we take t1 as a separating region. Let's say x1, right? So can be separate, it can be split into two parts, right? Let's say x1 less than t1, x1 more than t1. So if x1 less than t1, so the separating region, there are two separating region, right? Based on x2. So we have x2. Okay. Oh, sudah. Boleh siapa-siapa kat dia keluar. Siapa yang berani? So this one x2 less than or equal to t2. Okay, thank you. Tak keluar boleh? Okay, continue. So if you look at this one, nampak this one? For x1 less than t1, so we have two separated region based on x2, right? x2 equal to t2. So when x2 less than t2, it means that it will cover region number 1. This is going to be R1. When X2 more than T2, it will cover region number 2. Right? And then now we complete on the left hand side. Let's look at on the right hand side, the region for more than T1. So when X1 more than T1, we can separate the region by X1 based on T3. Right? So this one going to be X1. Right? We can separate X1 based on T3. X1 less than or equal to T3, X1 more than T3. So when X1 less than T3, we will conclude region number 3, right? And when X1 more than T3, so if you can see from the partition region space, we can separate the region based on X2, right? So this one going to have another separation based on X2. So the separation will be, the separation rule will be based on X less than or equal to X T4, X2 more than T4. When X2 less than T4, we will conclude region number 4. When X2 more than T4, it should be region number 5. Right? So this is how we transform from partition region, partition space to decision tree. Thank you very much. Right. Jauh you jalan. Okay, this one okay, clear? Clear this one? Right, let's look at another example. Let's say we look at example regression tree number 4. Right. So basically I already showed the answer here. Okay. So now let's say we have several region, right? This is region number 1. Maybe I put like this. This is R1, R2, R3, R4, R5, R6, R7. Right. So the value of R, right? Basically, we take the average of the data. This is the average of data 0.5 for region number 1, region number 2, 0.807. Right. So first thing to do is we look at the line that separate the whole data, that have a complete line through the region, right? So for this example, at this point, like X2, maybe this is 0.3 lah, kan? Maybe 0.3. So the first variable that separate, which is the root node, X2 lah. X2 can be split into two regions, where X2 less than or equal to 0.3 and X2 more than 0.3, right? So when X2 less than 0.3, right, it can be separate, it can be split by X1. So X1 next, X1. So for X1, if you can see from the partition region, it can be split by 0.8, right? So it split two region by 0.8. So when X1 less than or equal to 0.8 and another one is X1 more than 0.8, less than 0.8 should be region number 2. More than 0.8, region number 1. Do you understand this one? This one we want to transform partition space to construct a decision tree. So this is for left hand side. For the right hand side, so we have basically 1, 2, 3 complete line that separate region for X left hand side, right hand side. So let's say we pick this one, right? where x2 equal to 0.9, for example. Maybe this is 0.95, this is 0.5, right? And then this is 0.5, for example. Right? So let's say we take this one, 0.9. So when x2 is more than 0.3, right, it can be separated by x1 at 0.9. So let's say this is x1 can be separated by 0.9. When x1 less than 0.9, x1 more than 0.9. Right. For x1 more than 0.9, right? More than 0.9, there is another separation, kan, based on 0.95, right? So this one can be separate another value, which is 0.x1 more less than 0.95, x1 more than 0.95, right? So this one should be more than less than 0.95 is region number 4, more than 0.95 is region number 3. So this one going to be region 4 and region 3. Right. Boleh? So now that is for more than 0.9. Now we look at less than 0.9. So less than 0.9, so x1 can be separated by at 0.5, right? So this one, another separation, x1 can be separated at 0.5 and x1 more than 0.5, right? For more than 0.5, only one region, there are no separation, R5. Right? More than 0.5, R5. If the x1 less than 0.5, you can separate another two region where x2 less than 0.5 and x2 more than 0.5. Right? So this one going to be x2 less than or equal to 0.5, x2 more than 0.5. So more than 0.5 is region number 7, less than 0.5 region number 6. Right. So this is how we transform from partition space to decision tree. Right. Now, of course, the end value will be the mean for each region. So region number 1 and region number 2, the mean is 0.87. 0.827. And so on, you input the value of mean inside the leaf node. Okay. Any questions so far? No? Clear, right? So now let's look at another example. Example 1A. So how to transform this partition space to decision tree diagram? So let's look at this one. The complete line that separates between two areas, T1 and T2 at x1. Right? So we have two lines here, T1 and T2. T3, sorry, for x1. Right, so let's decide the first split based on x1. Right? So let's say this is x1 less than T1, x1 more than T1. Right? So for x1 less than T1, we can separate the region into two parts based on x2 equal to T2. Right, this is going to be x2. x2 less than t2, x2 more than t2. Right, for x2 less than t2 is r1, x2 more than t2 is r2. Right, so this one settled already. Now we focus on the right hand side. For the right hand side, it can be separated into two parts by x1 equal to t3. Right, so this is going to be x1, x1 less than t3, x1 more than t3. Right, so for x1 less than t3, it should be r3, region number 3. x1 more than t3, so we can separate the region into two parts based on x2 equal to t4. Right, so this is x2 can be split into two parts, x2 less than or equal to t4, x2 more than t4. So for x2 less than t4 is r4, more than t4 r5. So this is a decision tree diagram based on the partition space. Any questions so far? No. Right. So before we proceed, please make sure you sign in your attendance. Now let's look at another example. Example 1b. So from tree diagram, we want to transform it to partition space. Right. So look at the root node. We have f1. Another variable is f2. Right. So let's say this is f1 and this is f2. So for the root node, the decision rule is based on when f1 less than 5, less than or equal to 5, another one f1 more than 5. So the splitting point is 5. So this one, let's say I make it a rectangle. So this is a separating region. Right. So when f1 more than 5, there are no further split. Right. So this area on the right hand side is a green area lah. Okay, this is a green area. Okay, so on the left hand side can be split by f2 equal to 4. Let's say this is 4 and this is another region, right? When f2 less than 4 is a green area. If f2 more than 4 is actually a pink area. Okay. So I have another example, C, D, and E. So I leave it to you to complete by complete later lah, huh? Okay. So or you want me to show another one? So I show the last one lah, C, right? One C. For D and E, you need to do by yourself lah. Okay. Now let's look at this one. So we have two complete separated area, right? Betul? This is maybe this is 150 and this is 250. This is negative 50. This is 0 and this is 400. Right. So let's choose this one as a separating point, which is a root node. So this is x1 and this is x2. So let's say x1. So we can separate it by when x1 less than or equal to 250. Another one is x1 more than 250. So when x1 less than 250, so it can be separated by x1 again at point 150. Right? x1 can be separated by x1 less than 150. Another one is x1 more than 150. Right? So for x1 more than 150, it should be equal to R3. When x1 less than 150, we can separate the region based on x2 at negative 50. So this is another separation at x2. What is the splitting criteria? x2 less than negative 50, x2 more than negative 50. For less than negative 50 is R1, more than negative 50 is R2. Okay, I think very simple, isn't it? So on the left hand side, okay, clear. Now focus on the right hand side. On the right hand side, when x1 more than 250, we can separate it into two parts, right, based on x2 equal to 0. Right? First part, second part. So x2 less than or equal to 0, x2 more than 0. When x2 less than 0, there are no further separation. This is going to be R4. When x2 more than 0, we can separate the region into two parts, which is x1 at x1 equal to 400. So x1 less than equal to 400, x1 more than 400. More than 400, less than 400. Less than 400 is R5. More than 400 R6. That's all. Okay. For example 1D and 1E, I think you can do by yourself. Huh? Any questions so far? No question? Sudah Tera already? So, Latera boleh ambil test number 2. Right. So, regression 3 building process. So, now let's look at, as we discussed just now, there are two parts that we're going to discuss in this decision tree. Regression tree and classification tree. So, first part, regression tree. So, what is the process? First, we will segment the predictor into a number of simple region, and then we will make a prediction based on the mean of the training data in the region to which it belongs, right? For example, we want to predict a response of class Y from the input X1 until XP, and then we're going to draw a binary tree, apply a test to one of the input, right? And depending on the outcome, right, we go to either left or right, and then eventually we'll come to the leaf and make a prediction based on the aggregate value, right, which is the mean and standard deviation, and we will calculate. If you use software, it will calculate for you the mean square error, right? So now this is the same thing I explained just now. It's the same thing. It's a procedure one by one. First, we divide the predictor space, and then right? And the goal is to find box R1, R2, and Rj that minimize the residual sum of square, right? the minimum value of sum of square. So that one going to be our ultimate value lah, right, for prediction. And as I said just now, we will do a top-down method. I begin with the top of the tree and split the predictor space. Each split indicate a new branch further down to the tree, right? From the root node to the leaf node, right? So let's go for example. But before we go for example, let's look at the application example. Right, this is a heater data set. We have 322 observation and 20 variables, right? So the variable that from 20 variables, I want to focus on 3 variable only, which is salary. The goal is I want to predict the salary based on experience and number of hit, the salary of players lah. So this is example of tree diagram lah. It can be split by years, right? So means that years is the important variable that explain explain salary and how much salary should be given to the players, right? So determined by the first variable, which is years of experience, right? So if years of experience less than 4.5, so the salary will be 5.11 thousand, right? If the years of experience more than 4.5, we will look into the number of hit. Number of hit more than 117, so the salary will be 6.74, right? Multiply by 1,000 lah. And if less than 117, should be 600. So this interpretation, this way of interpretation is quite easier compared to linear regression and logistic regression, right? So this is the example lah. It's the same explanation as previous lah. So let's look at this one. If we look at the first variable that split the whole nodes, right? This variable is considered as very important variable, years of experience, right? So if the player has less experience, means less than 4.5, the salary should be given 160,000. If they have more than 4.5 years, we will look at the hit count. If the hit count less than 117, salary should be given 400,000. Example number 2 ni, right? So we want to do a regression tree, right? So why this is a regression problem? Because we have 4 variables, 4 independent variables, x1, x2, x3, x4, and we want to do a prediction on golf players. And this golf player is numerical, right? For numerical, remember linear regression, dependent variable should be numerical, independent variable can be numerical or categorical. For logistic regression or classification method, dependent variable should be categorical, independent variable can be either numerical or categorical. Right. So now, to draw or to perform a regression tree based on this data, first thing to do is step 1. Right, we need to calculate standard deviation for whole data. Right. So now before I go further, right, to determine the root node for regression tree and classification tree, there are several methods available. For regression trees, first method, one option is variant reduction, another option is f-test. So for classification trees, we have Gini index, we have entropies, and chi-square, right? So this is regression problem, right? So we will focus on variant reduction method. So first step for variant reduction method, we need to calculate standard deviation for the whole data, and then we will calculate standard deviation reduction, right, for each of independent variables, right? And based on reduction value, standard deviation of reduction, and we will choose the highest value to be selected as root node. Okay. Now, first step, calculate standard deviation of whole data. So we need to input this data into calculator, calculate standard deviation. We before we calculate standard deviation, let calculate mean 25 plus 30 plus until 30 divided by how many observation? 14, right? Right. So we will get 39.79, right? And then we calculate standard deviation for population. Standard deviation, I think this is not standard deviation. This is with this is variance, right? Variance. That's what we call it as a variance reduction. So x I minus x bar square divided by capital N. So this is a population variance, right? So in this case, population variance should be equal to 9.32. So this is the global variance for the data, the whole variance of the data. Next step, I will cut short because it's going to be very long. Next step, we will calculate individual variance. Right, individual variance. For example, we have four variables. Okay, the first variable is outlook. We do for the first variable first. First, we have sunny, and another one is overcast, and the next one is rain. Right. So you need to calculate the standard deviation or variance for sunny. Right. Look at this one. We take sunny. This is sunny value. Right. So we will find standard variance for 25, 30, 35, 38, 48. Right. So you need to calculate that standard variance. So this is variance for sunny. Let's say so. Let's say I put this in this box lah, so we can understand. Right. For variance for wait, this is not variance. Sorry for yeah. This is standard deviation, betul lah. boleh buat correction balik. This is standard deviation, not variance. We will calculate standard standard deviation. Actually, we should calculate variance, but basically it's the same. We will give the same result lah. This is standard deviation. Right. So standard deviation should have the square root. Yeah. Okay. That's all. So we will get 9.32. This is the value of standard deviation, not variance. Okay. So the standard deviation for sunny, right, for sunny should be 7.78. I think later you can reconfirm my calculation. You calculate this value and find standard deviation. So we have n equal to how much? 5 observation for sunny, right? For overcast we have 3.49 and n equal to 4. Rain we have 10.87, n equal to 5. So this is standard deviation for each category, right? For sunny, overcast, and rain. Next, once you already have the standard deviation for each category, this is step 1, step 2, right? For outlook. So we need to calculate standard weightage standard deviation. Weighted standard deviation, right, for outlook. So how to calculate weightage standard deviation? Based on the formula summation of Ni divided by capital N multiplied with standard deviation, right? So in this case, we have 5 observation for sunny out of how many observation we have? 14, right? So 5 over 14 multiplied with the standard deviation 7.78 plus 4 over 14, 3.49 plus 5 over 14 multiplied with 10.87. So this one should be equal to 7.6589. So I think you need to reconfirm my calculation again later, okay? This is step number 2. Step number 1 is calculate the standard deviation for each category. Step number 2, we calculate the weighted standard deviation. Step number 3. Step number 3, we need to calculate the standard deviation reduction. Standard deviation reduction is based on overall standard deviation minus weighted standard deviation. Right? So overall standard deviation is 9.32. Remember this one? Right? 9.32 minus weighted standard deviation 7.6589. So this one should be equal to 1.66. This is a standard deviation reduction for outlook. Right? So we have 4 variables: outlook, temperature, humidity, and wind. So we need to calculate for all. Okay, so this is one. So let's look at another one, which is temperature. Right? It's the same process. Okay. So for temperature, so we have hot, mild, and cool. Okay. So we need to calculate the standard deviation for each category. Right? Mild, starting from hot. This is standard deviation. and N. Mild and cool. So for hot, we have 8.95. Later you can calculate by yourself. Huh? We have 4 observation, 7.95 and 10.51. This standard deviation is calculated based on the population formula. All right. So next, we have the standard deviation for each category. Step 1, this is step 1. Step 2, weighted standard deviation. Right. So we have 14 variable data, 4 over 14 multiplied with 8.95 plus 6 over 14 multiplied with 7.95 plus 4 over 14 multiplied with 10.51. So this one should be equal to 8.84. Right? And then step number 3, standard deviation reduction. Right, standard deviation reduction 9.32 minus 8.84. This is equal to 0.48. Okay. Right. So this is number 2. Right. To cut short, you need to calculate for humidity and wind. So I'm going to give you the final answer. Right. So you need to repeat the same procedure for humidity and wind. So now this is standard deviation reduction. So we have outlook and temperature, humidity, and the last one is wind. So for outlook is 1.66, temperature is 0.48, and humidity you calculate by yourself later on to 0.27, and wind is 0.28. Okay. So to select which variable going to be root node, so we look at the highest, right? To decide the root node, choose the highest standard deviation reduction. So in this case, outlook going to be our root node. Okay. So now, right? So we need to decide, draw the decision tree. This is outlook. Right. Outlook, we have 3 categories. The first one is sunny. The second one is overcast. The last one is rain. Right? So for sunny, there are 5 over 14 observation. For overcast, we have 4 over 14. Rain, we have 5 over 14. Okay. So in constructing decision tree, right, we need to have a stopping rule. right? If we don't have a stopping rule, then we will grow tree until don't know what extent lah, right? So we need to have a stopping rule. So our stopping rule is when the number of observation on that category less than 5, right? Then kita stop. If more than 5, we need to continue finding the splitting node. Okay. So in this case, overcast less than 5, right? So then we will look at the data. Look at the data. Oops. For overcast, this one, overcast, 1, 2, 3, and 4. Right. We take this value 46, 43, 52, and 44. Right. We will calculate the average of these 4 values. Right. Average of these 4 values. Okay. So that one going to be how much? 46.25. This is 46 x bar equal to okay. Now, since Sunny and Rain have observation more than or equal to 5, so we need to find the splitting node, the next variable to be on the child nodes, right? So Sunny, right? So let's look at the data outlook. So we have Sunny, we have 5 data, right? Sunny, right? Temperature, hot, hot, mild, cool, mild. This is humidity. The first is 25, 30, 35, 38, and 48. So this is the data set for Sunny. Outlook equal to Sunny. So you can sort it from the original data. Okay. So again, we need to select, since the data, the number of observation is equal to 5, right? So we need to find the next splitting nodes, right? The next nodes. So again, we need to repeat the same process. First is for temperature. But before that, we need to calculate the standard deviation, overall standard deviation. This is our very first step. So overall standard deviation should be, in this case, you calculate by yourself later on, 7.78. Right. So for temperature, we have hot, mild, and cool. Right. So for hot, we have 2 observation. So if you have 2 observation, then you can calculate standard deviation. This one should be equal to 2.5. This is standard deviation. This is n. We have 2 observation. For mild, we have 2, right? 35 and 48. So this one should be 6.5, 2 observation. For cool, you only have 1 observation. So If you have only one observation, there are no standard deviation. Right? So deviation should be equal to 0, only one values. Right? So in this case, calculate weighted standard deviation. So it should be equal to how many data we have? 5, right? 2 over 5 multiplied with 2.5 plus 2 over 5 multiplied with 6.5 plus 1 over 5 multiplied with 0. This is equal to 3.6. Next, reduction. Standard deviation. So basically standard deviation reduction. So 7.78 minus 3.6. And you repeat the same step. So next we compare standard deviation of reduction. But assuming that you already calculate for humidity and wind, so this one I'm giving you the final calculation lah. Huh? So this is temperature, humidity, and wind. So the temperature, this one should be equal to 4.18, right? 4.18. This is 3.33, and this is 0.85. So comparing the reduction of standard deviation, right? So the next splitting variable for sunny is temperature, right? So we input into the diagram. So this one going to be temperature, and we divide into 3, which is hot, mild, and cool. Right. The data here, if we have 2 over 5, this is 2 over 5 and only 1 over 5. Okay. Same procedure for rain, right? For rain, you need to do the same procedure, right? Maybe I'm giving you the final answer, right? This is for rain, right? So compare standard deviation of reduction. So we have temperature, humidity, and wind. So this one 0.68, 0.38, and the last one 7.62. So wind will be your splitting node for rain. So this is, oops. Temperature we have 2, right? Either weak and strong. Weak or strong. Okay. Right. So next step, what we need to do is we need to input all the average value, right? So this is the average value for overcast, 46.25. For sunny, hot, we have X bar equal to 27.5. Sunny, mild, temperature mild is 41.5. Sunny, cool, X bar equal to 38. This is X bar equal to 47.67. X bar equal to 26.5. Do you know how to get this value? Right, for example, 27.5 here, sunny and hot. So we need to go to our data, look at sunny. Right, so we have 5 observation. Right. So, but we look at the sunny and hot. So we have only 2 observation, right? So we take 25 plus 30 divided by 2. So we will get 27.5. Okay. So this is how we construct perform a regression tree using variance reduction method. Any questions so far? So please pay attention. Maybe this kind of question will be in your final exam. It may be. Any question? No question? Should we take a break? Okay, we take 5-minute breaks. Let's continue on next part. Just now we look at regression tree. Now we continue on classification trees. Right. So what is classification trees? Classification tree is when you have categorical predictor data. Right. We want to predict the categorical data. So that one falls under classification trees. Right. Just now we look at prediction on numerical data. That is regression trees. For classification trees, we want to predict categorical data. Right. So it built through a process known as binary recursive partitioning. This is important term. So it developed based on binary recursive partitioning, right? So classification and regression tree are powerful tool for analyzing data lah. So when we are dealing with qualitative output variable, then we can use classification tree or any classification method, right? But in this case, we are looking into classification tree lah. So observation will be classified in the most commonly occur class or training observation in the region where it belongs, right? So now, for regression trees, right, the end product or the leaf node, we are looking into simply average of the data that belong to that category. Data fit well in that category or not, right? So we choose the lowest mean square error among the leaf available. So the mean square error can be computed by using any statistical software, like Python, R, SPSS, and so on. Right, but I'm not going to show you how to compute mean square error for regression trees. But that is the measures that we use to determine which leaf is the best to predict outcome, right? But in classification trees, right, we use error rate, classification error rate, to know which class is the best predict outcome, right? So we're going to choose the lowest error rate to determine or to conclude that that class is the best leaf for our outcome. Right. So the error rate can be determined by 1 minus the maximum of proportion, right? So let's say we have sunny. Let's say we have the last example. We have rain, right? In rain we have weak and strong. Okay, remember tadi weak and strong. So the proportion for weak and proportion for strong. We need to measure the proportion. Let's say this is 4/14. This is maybe 9 or 10 over 14, right? So this is the proportion. So proportion means that the number of observation divided by total number of observation. Right? And then we choose the maximum, 1 minus the maximum of proportion is the error rate. So now, finding the best split, right? As I said just now, for regression trees, right? We use reduction in variance, reduction in standard deviation, and another one is F-test. For classification method, there are three popular methods. First is chi-squared test with log-word measures. Another one is Gini index. It's also known as population diversity. And last one is entropy. Entropy is also known as information gain. So basically all of these going to measure the purity of the class, right? So this is a formula for entropy and Gini index. So we will focus on entropy and Gini index for this subject. We're not going to regression tree. So classification and regression tree card is introduced by Bremen in 2001. Right. So you usually use Gini index to measure the split point. So entropy, summation of negative proportion multiplied with log proportion base 2. Right. For Gini index, 1 minus summation of proportion square. So entropy measures set the disorder level, and Gini impurity quantify the probability of misclassifying instance, right? So this is a same thing. Now let's look at example number 4. How to calculate entropy for this data. Right. So in this data, we have two variables, A and B. So this is x1, x2. This is our y, which is dependent variable. In this case, y is categorical data. We have positive value and negative value. Positive class and negative class. For A and B, we have true and false. So first step to calculate entropy, or to know which variable going to be our root node, same procedure as in regression tree. First step, we need to construct cross tabulation table. Cross tabulation table. So for for A, variable A, so we have class A equal to true, A equal to false. Maybe I put A equal to T, A equal to F, and this is total. And class, we have positive class, negative class, and total. So this is cross tabulation table. Right. Right. So overall data, how many observations we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 observation. Out of 10 observation, we have 1, 2, 3, 4 positive class. Right? 4 positive class, 6 negative class. Okay. Now remember we are looking into A. So when A equal to true, how many A equal to true? 1, 2, 3, 4, 5, 6, 7. So we have 7 A equal to true and 3 A equal to false. Right. So now, next, we need to measure how many A equal to true and class positive. 1, 2, 3, 4. Right? We have 4 A equal to true and class positive. And the balance is 3. A equal to false and class positive. A equal to false, class positive. We don't have any. Right? We don't have any. So it's equal to 0. A equal to false and class negative, all 3 values. Right? So this is for A. If you have, then you need to compute for B lah. Right? Do the same thing, construct a cross tabulation table for B. Right? So this is C plus minus total. This is B equal to true, B equal to false, and total. So you do a table properly lah. This is equal to 10, 4, and 6. So how many true value for B? 1, 2, 3, 4. The balance is 6. Okay. So true value positive 1, 2, 3. So we have 3 and 1. Right? False positive 1, only 1. Right? And false negative equal to 5. All right. Now, the formula, this is this procedure we want to calculate entropy, right? We create more space. So remember the formula of entropy is summation of negative PI, which is proportion multiply with log proportion base 2. So the overall proportion for positive we have 4 out of 10, right, which is equal to 0.4. This is proportion for positive. Proportion positive. Proportion negative, we have 6 out of 10, which is 0.6. So now we need to measure entropy for all. Or we can put it as entropy overall equal to negative 0.4 log 0.4 base 2 minus 0.6 multiplied with log 0.6 base 2. So this one should be equal to 0.9710. So remember, this is the overall entropies. This is same procedure, same step as we do in regression 3. Remember, regression 3 we compute overall standard deviation first, right? And then we compute individual standard deviation. Now, step number 1. No, this is step number 1, right? This is step number 2. Step number 3. Compute entropy for A. Right? Entropy A equal to true and entropy A equal to false. So A equal to true, same process, same formula. Right, same formula. Let me highlight with this color. Right, same formula. So When A equal to true, we have 7 out of 10. Right, sorry, A equal, sorry, this is A equal to true. When A equal to true, we have 7 observation, right? So 4 positive, 3 negative. The first one is 4 negative 4 over 7 log 4 over 7 base 2 minus 3 over 7 log 3 over 7 base 2. So this one should be equal to 0.9879852. Another one is we have 3 FA equal to false for positive 0, negative 3. So negative 0 over 3 log 0 over 3 base 2 minus 3 over 3 log 3 over 3 base 2. This is going to be 0. Right. So that is entropy for A equal to true, A equal to false. Next step. Step number 4. So we need to calculate information gain for A. Right, information gain for A. So information gain is equal to, for A, right? So entropy overall minus summation of proportion of entropy AI. Right. So for A, we have 7 out of 10. Right. So entropy overall is 0.9710. Right. For true, 7. For false, we have 3 observation. Right. So the proportion for true, the first one is true, right? So we need to find a proportion for true. A equal to true, A 7 divided by 10 multiply with 0.9852 minus this observation for A equal to false. We have 3 out of 10 multiply with 0. So this one should be equal to 0.28136. Okay. Right. This is how we find entropy for variable A. For B, same procedure. We just repeat the same way to find B. So let's look at this one, B. Right. So entropy for B equal to true. So let's look at this one. We have B equal to true. 3 over 4 and 1 over 4. Right. The proportion is 3 over 4 and 1 over 4. So negative 3 over 4 log 3 over 4 base 2 minus 1 over 4 log 1 over 4 base 2. So this one should be 0.8113. B equal to false. We have 6, 1 over 6 for true, 5 over 6 for false. So negative 1 over 6 for positive class, log 1 over 6 base 2. For negative class, 5 over 6 log 5 over 6 base 2. So this one should be 0.6500. So next step, we need to find the information gain for B. So same procedure over entropy overall minus summation of proportion for true and positive, true and false entropy BI. So this one should be 0.9710 minus, what is the proportion for true? 4 over 10, right? False is 6 over 10. So 4 over 10 multiply with 0.8113, right? And minus 6 over 10, 0.6500. So this one should be equal to 0.2565. Right. Remember regression tree? How to choose the root node? Pick the largest standard deviation. For this one, we're going to choose the largest entropies and the largest information gain. So since information gain A is larger than B, right? A is a 0.28, how much? 28136, and this one is 0.2565. So A will be root node. Okay, that is just an introduction to the classification tree. We will continue next week. All right. Any questions so far? No. All right. Thank you very much. Assalamualaikum.